Okay. Um, I think we should start. I'm already late. Sorry for that. No need to introduce me. So that's fine. Um, so we can have a short lecture of about 40 to 45 minutes today. And tomorrow also I'll try to take some lectures. I was lately busy with interviews and other things, so I couldn't come on time. So now we will have an introduction on hydrodynamics and magnetohydrodynamics. So basically, which comes under something known as the astrophysical fluid dynamics. So what do we study in astrophysical fluid dynamics? That is the first question. So here you can see the image of a spiral galaxy. Okay, so the question that you have to ask yourself: how to study this type of system? How to study the evolution of this system? Um, whether can you invoke a theory of fluids to study the evolution of this system, or you need some sort of n-body simulation, n-bodies interacting with each other, and then study this type of system. So the question is, under what scenarios we can invoke the theory of fluids. And so basically how to combine astrophysics, how to study the dynamics of galaxies, and in our case, let's say stars, stellar atmosphere, using fluids. So that is the question. So that's what I hope we will be able, or you guys will be able to understand after this lecture. So if you look at our solar system, so we have sun and then we have so many planets. The question is like whether you can study this system using the equation of fluids or not. Okay, so that is another question. For galaxy, you might have heard that people use the equation of fluid mechanics, but for solar system, can we use it or not? So that is another question. By the way, I am trying to present so I didn't get time to make the slides. So these are the slides from the coursework that I take here for 3 months. So I will try to condense all those things in probably 30 minutes. So I will move fast. So how do you describe this system, as a system of particles or the fluid? And there is a difference between these two approaches. Can you tell me what is the difference if you use just, let's say, n particles and then the fluid? Of course, fluid consists of particles only, right? It consists of, let's say, n particles. So what is a difference in the physics? Sorry, one by one. System and in the fluids. Well, that is a macroscopic description of a fluid, but in the microscopic, you can invoke kinetic theory where you have individual particles also, right? It depends on the densities. So there's very important physics when you consider a system of, whenever you invoke equation of fluid, and that is the pressure that comes into the picture. And we will see that in the equation of motion, which is basically the second law of Newton, in case of the fluid, the pressure will appear in the equation, while in case of simple particles, probably you will have the collision terms and other things, but not really the pressure. So the pressure is something which is very important, and that distinguish, that's where the entire physics is. And as you rightly said, sometimes we define fluid as a continuous medium with a well-defined macroscopic properties, but that is a macroscopic description of the fluid. Microscopically consists of several particles. Okay, they are interacting with each other, and that is actually giving rise to the pressure, something known as. Okay, so how do you define? So in the fluid, let us say I have 3 different states of matter: solid, liquid, and gas. So how do you distinguish between the solid, liquid, and gas? That's very easy. So I'm not going to ask you questions, or they won't be able to complete the lecture. So solids have constant surface area, constant volume, and of course they resist the shear stress. If you have read the Feynman lecture series, so you know that this is a very, very important property. So you have this is a solid, and the shear stress will be the stress in this direction, right? So if you apply the stress, it will resist it. Okay, but if you apply enough stress, it will break. So that is a different thing that will change the property. If the stress is more than the elasticity, then of course it will break. But then in general, they resist the shear stress. So what happens in the liquid and gas? Of course, both have variable surface area. But the distinguishing feature is that the liquid has constant volume, right? If you have 1 liter of water, it will remain 1 liter, whether you pour it over glass or or pour it in a tank or anywhere. Okay, so volume remains same, but that is not the case in the case of gas. For example, if you have gas confined in a cylinder and you open the cylinder, it will quickly occupy the entire room. So the volume will also increase, although density will go down. Okay, but both of them will continuously deform under the shear stress. So if you apply a shear stress, or if this would have been I mean, if you have a glass of water and you apply a shear stress like that, it will start flowing. Okay, and that's why those are known as the liquid, or basically fluids. So when we talk about the fluid mechanics, we are essentially talking about these two regimes. Okay, and one another distinguished feature is that the liquid is incompressible, all mildly compressible. Okay, and the gases are highly compressible. And then, you know, when you compress the gas, it liquefies, and that's how you get LPG, liquefied petroleum gas, right? Okay, so let's go. So these are different phases of matter. So we will be talking about liquid or gas mostly. Whenever I talk about the fluid, mostly it is gas. And then you know that with enough pressure, it can become liquid also. So, okay, this I have converted. Yeah. So I will just give you a brief introduction. What do I mean by it resists the shear stress? It means that when you apply a shear stress on a solid, it will just deform by a distance delta x, of course. And then if you remove this shear stress, it will again come back to its original position, unless and until you have applied enough shear stress that it deforms completely. That's a different thing. So in that case, the shear modulus can be computed by force per unit area and then divide by how much displacement is there, delta x. While in the fluid, it is not delta x, while it is delta u. That means once you apply a shear stress, they will start flowing with a particular velocity, and that velocity is given by the u, and that is, and then if you compute the quantity which, okay, I think it was showing my, this is unstable. Aries, or okay, it is connecting again. So yeah. So if you compute the similar quantities in terms of the fluid, you will arrive at a description what is known as the viscosity instead of the shear modulus. That's the idea. Okay, I would have preferred direct connection, but that's not here. The internal connection is unstable. It's trying to connect. Let me again. Yeah, internet is not working. नहीं, वो है नहीं. केबल लगा सकते हैं. अडेप्टर है आपके पास? अडेप्टर है? वाईफाई की स्ट्रेंथ कहाँ पे ज्यादा आती है? यहाँ ज्यादा आई है. Okay, let me try again if it works. वाईफाई ना, तो यहाँ रखता हूँ 1 मिनट. चल तो रहा नहीं है. Let me, हाँ अभी आ गया. So probably वहाँ स्ट्रेंथ कम है. Why this showing like this? Okay. Yes. So this we have discussed. So you'll get an expression similar to the viscosity. Now I'm not going into the concept of viscosity here, but you always remember whenever we are trying, whenever we will deal with dry fluids, that is a convention of Feynman, not mine. Ideal fluid, inviscid fluid, or perfect fluids. It all means that the viscosity is close to 0, which is mostly found in textbooks, but in reality, mu is always finite. Okay, so let me not go into this. So let me tell you. So there is an experiment run by Professor Thomas Parr in 1927, where pitch, it is used for making roads. So that was warmed and sealed in a funnel, and it was cooled down and allowed to flow since then. And it took 8 years for a drop to fall into the beaker. So what I'm trying to say is whatever was thought to be solid is now acting like a liquid. Why? because there was a shear stress here because of the gravity and the shape of the funnel, and it is not resisting the shear stress. But then you have to consider over a longer time period. For a shorter time period, it appears that, okay, it's like a solid, but a longer time period, it is liquid. And I think it's still running. And the last drop, I don't know when it fall down, but then, yeah, so it's still running. So the difference between the solids and liquid is sometimes depends on the length scale and the time scales you are looking at, okay? But not all the fluids are behaving like this. Not all the solids are do behave like this. Okay, this is a particular example. Okay. Okay, so let us say now that here comes the first hypothesis whenever you are studying the fluid mechanics, and that is known as the continuum hypothesis, and it makes our life easy because then you'll be able to use the simple equation of motions given by Newton, you modify them, and then you study those things and you apply those things in fluids. So the first hypothesis is that continuum hypothesis. It says that although the fluid consists of particles that we have already discussed, but if you are working at the length scales, for example, whenever you are trying to do the physics, or you're trying to design an experiment, or you want to study a system, you always look at the length scale and time scales you are looking at, right? If you want to study the galaxy evolution, we'll be looking at megaparsec length or the parsec length scales and thousands of year time scales, right? For universe, it will be even longer. For sun, it is a small length scales, let's say for 100 of kilometers, and probably seconds of time scales. So it depends on what length scale and time scales you are looking at, and that is determined, that is dependent on the problem you want to study, right? So so here the dashed line tells you the approximate intermolecular distance in air. So for example, air in this room. So what is the intermolecular distance? So if you have two molecules, what's the distance, or what's the volume between them, or what's the volume enclosed by these particles? So if you are investigating the length scale, so if you are concerned about the physics that is happening in the length scale is smaller than that, okay, and let's say you want to study the density, how the density varies in a length scale or in a volume is smaller than the interatomic distances, let's say intermolecular, basically, then your density will widely fluctuate, right? It's because you have you can fix a volume here, which is very small, smaller than the volumes of a single particle. Then a particle may strike here or may not strike here, and then suddenly when the particle will come into that region, density will increase. And when a particle will go out, density will decrease, and then it continue to happen like that. Now you are trying. Now you continue to increase your volume more and more. Then at some point, when you have enclosed enough particles inside the volume or the volume of your consideration, then even though some particles are leaving and because some particles will obviously leave the volume, but at the same time some particles will enter into the volume. So what happens overall, your densities will remain same. Okay, but then if you go even to a larger length scale, then density might changes. So these changes are because of the microscopic uncertainty, and these changes are because of the macroscopic. So where can you see this change in the room? So it can be seen in terms of temperature. If you go very close to these bulbs, where so temperature could be large, and if you are away from it, temperature could be small. So these are these macroscopic uncertainties, not the microscopic one. Okay, so what does the continuum hypothesis says? So the continuum hypothesis says that you can consider fluid as a continuum. Okay, not composed. Then you don't have to worry about how each and every particles behave. Okay, so you can consider it to be continuum if the total number of particles and enclosed multiply. This is the number density basically. So number density multiplied by the probe volume is much greater than 1. That it means that you have enough particles. You are studying the region containing enough particles. If that is the case, then you can assume fluid to be a continuum. Yeah, so this is something that I have mentioned here. Yes.
You're saying that the density of a fluid is dependent on the volume element that I choose.
The density, the density that you measure is dependent on your probe volume. Yeah, it depends on your probe volume. Yeah. Okay. So so this is basically the relationship This is a macroscopic length scale should be larger than the length scale that you are considering, should be larger than the mean free path, which is lambda, and that is anyway larger than the molecular length scale that we know. So this is the relationship. So whenever this is satisfied, that L is greater than this or L is maybe greater than this, then you can use this continuum hypothesis for your for understanding the physics of the fluid. Otherwise, you cannot. So that's where the migration from microscopic to macroscopic quantities happen. So yeah. So if you are here, probably here you need to use if you are in this region, probably you need to use kinetic theory of gases. Okay, because you are not still in the you're not you cannot consider fluid as a continuum. Okay, so how suppose you have kinetic theory. So kinetic theory is a complete theory basically. So what you do is, in case you have very large particles, you can still use kinetic theory. It's just that it will be very, very difficult to solve because you have so many particles interacting with each other, right? So what you do is, as a physicist, we try to average over the quantities and try to arrive at the simpler quantities such as pressure, temperatures, velocities, rather than dealing with each and individual velocities of each and individual particle. So that is always defined in terms of the distribution function, right? So there is a distribution of speed of air molecules in this room that is given by Maxwell-Boltzmann distribution. Okay, if you wanted, if you think that you can consider fluid as a continuum and there are enough particles, then you can actually calculate what is the density of those particles. Now you don't have to study the individual the probability density function here. Instead of F, if you average it over a volume, what you get is the density. Okay. Similarly, energy you can get in a similar fashion. You have half mv square, and this is the interaction energy between the potential energy, which is the interaction energy between two particles. And this is momentum. You have velocity. It's like calculating the moments, different moments of the function. And once you have, and it can also be written as average density multiplied by average velocity. So average velocity can be computed from here because you have capital M also, average mass, and then. And that's how we get macroscopic quantities from microscopic quantities using this type of averaging. Okay, so now onwards we will use all macroscopic quantities in this course, so that we can understand fluids in an easier manner. Okay, so before we go there, you also need to understand there are different type of flows in fluids. So these are some of the definitions that you should keep in mind whenever you are reading about book on the fluid or book on MHD. One is the steady. Steady means the properties are independent of time. Unsteady means, of course, dependent on time. Laminar, then it means that how should I tell you? I mean, the laminar means that the fluid parcel will follow a particular path. Okay, and that path is predictable. It's not that it's unpredictable. It's not like that. So that is known as a laminar flow. In turbulent flow, it is not a definitive curve, and it is not. It is also unpredictable. It is chaotic. Okay. Uniform means it has equal velocity, different velocity. Incompressible, you know, when it has a constant velocity. We'll come to this why it is so. And rotational means that del cross V is not zero. That means you have a vorticity in the system. So those are known as the rotational field. Irrotational means curl of V is zero, basically. So there is no vorticity. So, okay, shall I go into this? Let's not go into this. Let's not go into this. Now let me go back. Okay, no. So these are very advanced concepts, which. So let us start from here. So now you know that we are dealing with the macroscopic quantities only. That is density, temperature, velocity. And those are the average quantities, not the velocity of an individual particle. So whenever now I say that we are studying the evolution of density, that means density of a fluid parcel rather than a fluid particle. Okay, so we have to use the word parcel here. But before going into that, you need to understand the difference between Eulerian and Lagrangian coordinates, which is often used in fluid mechanics a lot. And there is a reason for this, because sometimes you wanted to study the evolution of the system standing at a particular place, or at other times you wanted to study the evolution of a system moving with the fluid, moving along with the fluid, right? So in these two different cases, you have two different types of two different ways of studying it, and that comes from the partial and total derivative. Okay, so assume this capital D is basically the total derivative. Okay? So you have a function. This function could be anything. It could be density, let us say. So this is the density, and density is a function of x, y, z, and t. Okay, so density is different in different spatial locations, and it's also changing with time. Okay, then in this case, you can open up this derivative, and it's very easy. What you have to do is you have to partially integrate it with each and every dependent, with each and every independent variables, and then you have to multiply by total. That is the simple mathematics, right? Okay, so this total derivative is known as the Lagrangian derivative, and we'll study the consequence of it. But if you do like this, you can always write it like this. This is a simple mathematics, and then you can rearrange it. df by dt can be written here, can be pulled here, and if you take this del f by del x plus del f by del y, del f by del z, it is basically the gradient of f. And you take dot product with dx by dt, dy by dt, dz by dt, which is the velocity. So it is del f dot u or u dot del f. It is one or the same thing. Okay, so you got this. So what is the meaning of this? First of all, let us understand what is the meaning of this part, del f by del, a partial derivative of f with respect to time. So what does it mean? Can anyone tell? At a fixed position. So basically here it is at a particular x equal to x naught, y equal to y naught, z equal to z naught, and those will change at different times. Okay, so you can think of it like you have like 100 of probes in this room at different spatial location, and what are they recording at every instant of time? So that is given by this function del f by del t. And what does this mean? It means that you see the gradient of f. F is a function. Okay, so that means gradients will tell you basically a change. Yeah, spatial change. Spatial change in the direction of velocity, where the fluid is flowing. Okay, so let's say so if everything is at rest, then of course, I mean, there's no point in studying it. Then you have the probe at different location, and this part is enough to compute the rate of change with time, right? But then if the things are changing, if it is flowing, if there is a spatial change, then you have to look at the gradient in the direction of the flow. Okay, this is the term. So so this term tells you the spatial change while the fluid is flowing. Okay, and these two constitute this total derivative. So the total derivative, so spatial derivative means you are at a particular location, and then how the quantity is changing at that location. That is given by this. Okay, this tells you not the change with time, only the spatial change, but in the direction of velocity, wherever your streamlines are. But combining these two, you get the total derivative. It means that now you are also see the change, or you are recording the change in the quantity f with time, as well as along the space. And which direction you should move? In the direction of flow, right? Because there's a dot product with this. So if the flow is in x direction, this gradient should, I mean, you have to move in that direction, right? So that means that this total derivative is telling you that once you are moving with the fluid, or you are sitting on a parcel of the fluid, how the quantities are changing, yeah, right? So these, and this is known as the Eulerian derivative. Okay, probably I must have written it. Yeah, and basically this term is known as advection, that you already know. The advection means that the change in the property of a function acted upon by a velocity field of the fluid, right? That's what we see here. Okay, so let us see some of the basic equation of the fluid mechanics. And one of the first equation that you will use mostly in HD or MHD, whatever you study, is the conservation of mass. Okay, there's a basic thing. The mass has to be conserved, right? So the trick is same. I'm not going into derivation, so don't expect me that to derive this. Okay, you do it on your own. I don't have even that much time to go into derivation. But the idea is very simple. You have a surface which is enclosing a volume. Okay, and then what it says is that the rate of change of density inside a particular volume can only happen. Remember, it can only happen if there is a intrinsic change in the density, or something is flowing into the volume, or something is moving out from that volume, right? Only in these two scenarios, the density can change inside the volume. That's what is the conservation of mass. Okay, so of course, we are also assuming that there is no external sources. I mean, there is no, for example, there is nothing external which is supplying the mass into it or taking away the mass. So there are no sources in sink. So of course, the rate of change of mass inside this V is equal to the outward mass flux through S, but with a negative sign because it is moving outward. So then you do where it's a simple mathematics. I mean, you can do it on your own. This is a dm by dt. Mass can be written as rho dv. It is the flux. Rho u is the momentum flux, basically, and is dot ds, and this should be equal. That is the mass flux, basically, not the momentum flux, mass flux. Rho u. Momentum flux will be rho uu. Okay, so so it is a mass flux through the surface S, and then you do this, and then you end up in getting this equation, and then you can write something like this. So this is the continuity equation, or the equation of conservation of mass. Okay, and you can also rearrange it because you know what is now what is the relation between partial derivative and total derivative. So you will end up in, I don't know whether I have it in the next slide. Yeah, I have it here. So what you do is, you know the relation between the partial and total derivative, all the Eulerian and Lagrangian derivative. You rearrange the things, and then you will end up in getting this equation. Okay, so you can use either of them. But this equation is very interesting. And it says that if the divergence of u is 0, okay, and you know what is the meaning of divergence? What is the meaning of divergence? Huh? So del dot u is 0 means? So in that case, what will happen? You can use from this equation. Density, the total derivative of density will remain constant. It can still change spatially. Okay. But the total derivative will not change with time. Okay, so that this type of fluids which show this type of behavior are known as the incompressible fluids. So why I'm saying this, because suppose if you want to do some sort of simulations or HD or MHD simulations, and you wanted to see the or you want to impose incompressibility, then you make sure that your velocity field, I mean the divergence of velocity field vanishes. Okay, so in that case you have so it doesn't mean that the density is constant everywhere. I mean, don't make this mistake. Okay, different fluid parcel can have different densities, but they remain same as the fluid flows. Okay, that is the most important thing. It doesn't mean that the rho is same everywhere inside. That is not the case. Okay, so then natural consequences, once you have conserved the mass, then you have to also conserve the momentum. That is a basic thing. So the conservation of momentum is basically nothing but the Newton's second law applied to the fluids containing a lot of particles, because you are choosing the macroscopic quantities. And whenever you are choosing, whenever you are working with macroscopic quantities, there is a property of the macroscopic property of the fluid that comes into picture, and that is pressure or temperature. Okay. So also, whenever we are deriving something, we assume certain conditions, and here we are assuming incompressibility, density is constant for all fluid element and all times. So these are some of the assumptions, but you don't worry about them. The idea is similar. You have a volume enclosing a fluid parcel. And then it has a area, you can take an area element, and there is also gravity. So gravity is acting like an external force. It may or may not present, and your equation will still be valid. Okay. So what you can do is, so you know that a force on an object can happen whenever there is a pressure difference, at least in case of the fluids. So if there is a pressure difference, so you take a volume. And if there is a pressure difference at two ends, what will happen? There will be a resultant force. And because of that, the parcel of the fluid will move into one direction or in some direction. Accordingly, if there is external force, such as gravity, because of the mass of the fluid parcel, it will again move. Okay, that will change the movement. So because of the pressure difference also, there is a force, because you know that the pressure is force per unit area. So there has to be a pressure difference. If the pressure is equal, of course, the net force will be 0. So so basically here we are calculating what is so F dot dn, you are calculating it here the pressure, and of course you know that it is always normal to the surface. So then you write like this, and then you use Gauss divergence theorem, and then you are saying that momentum is getting changed, or the rate of change of momentum is because of this pressure difference. Okay, if you apply these two things as well as due to the gravity, which is added here, gravity, pressure difference, or the gradient of the pressure. Basically, this is a tensor quantity, but we are not going into there. But the gradient of the pressure is equal to the rate of change of the momentum. Okay, so so then you end up in getting, I mean, you just solve it further. So you end up in getting something like this, and then okay, let's go to the final equation. So finally, you will get something like this. So basically, the rate of change of the velocity is equal to the external force that you are supplying plus the pressure, the gradient of the pressure. Okay. This is your homework, that why is there a negative sign here? This is a very interesting consequence of this negative sign. So you think about where the pressure is as and where the pressure is large, and then the motion will be in which direction. Yeah, exactly. Yeah. Yeah, opposite direction to the gradient where it is increasing, right? So so that's why there is a negative sign. So this is your, in very simple terms, this is your momentum conservation equation, and then you can further I mean use Eulerian derivatives, and then you will get something like this. Okay. Yeah, so I don't have time to explain it further. Let me see. Yeah, so this is the Euler equation of motion. Shall I tell you what is a conservative form? Okay, so these are not in the conservative form. So I will tell you what the conservative form is. So conservative forms tells you that the rate of change of quantity is equal to the rate of change of its or is equal to the flux of that quantity leaving that area or coming into that that volume, not the area. So those type of those form is known as the conservative form, but this is not in the conservative form. Where so it is the rate of change of the momentum density, but where is the momentum flux here? It's not present, right? So you can change it into the conservative form, but let me see if I can tell you that. So you see the momentum. So as I told you that this is del. The partial derivative of the momentum with time, you can write it like this. This is a tensorial notation, okay, using ijk, and then you can further open it up, and then you will get something like this. So it tells you it is a conservative form. So this rate of change of the momentum is equal to the, this is what? This is not d by dt. Del by del xj. So basically it's a divergence gradient, what it is, of the flux of this quantity. So it is a momentum density, so it will be a momentum flux. So the continuity equation was already in this form, where you have del rho by del t plus del dot rho v was there. Okay, so rho v was the mass flux. So here the momentum flux is this, and you see it is rho uu. So it is not a vector. It's not rho u square first of all. Okay, it's a dyad, dy. So it's known as the second rank tensor. So it's a second rank tensor, and it contains both the pressure. Its diagonal terms contain the pressure. Sorry, rho u square, which will add with the pressure, and the non-diagonal terms are shear stress. Yeah, exactly. Okay. Plus rho gi. Now you can tell me, you can say that, okay, this is not in the conservative form, but you can write it. You can write it in the conservative form anyway, if you use potentials instead of the force. So then, so these two quantities together, this and this, is known as the stress tensor, which can be replaced by a single expression, which is sigma ij. And then you try to open it up on your own, and you will realize there is a diagonal which contain the pressures plus rho u square, which is because of the motion of the fluid, and then you have off diagonal terms. Okay. So, or if you want some crazy notation, then you can also write it like this. This is the notation for dr. That means these two vectors are, this is not a dot product. That is outer product, exactly. And of course, when you are writing in terms of the matrices, then you have to write identity matrix here, which is 0 everywhere, only the non-diagonal terms survive. So basically, I mean, this is a conservative form. Why conservative form is important? Because again, if you do want to do some sort of simulations later on, then it is best to describe these equations in the conservative forms rather than using those forms. Oh, first lecture is over. Okay. Let's go to the, where's my second lecture? Okay. Yes. So, so the first one is the scalar equation that we have already discussed. The second one is the vector equation. So in a 3-dimension, how many equations we have? 3 equations, basically, ux, uy, uz, right? The problem here is that there is, if you wanted to study the, let us say, the velocities as well as density, okay. So in this equation, there is only one unknown, right? Basically, velocity is also, you can say, is unknown here. So basically, combining these two equations, how many unknowns you have? You have density and 3 components of velocity. How many? 4, and 1 pressure, assuming gravity, you know, for a system. So you have how many? 5 unknowns, right? 3 for velocity, 1 for pressure, and 1 for density. 5 unknowns. And how many equations you have? 4 equations. So 4 equations, 5 unknown. Can you solve it? So what should you do? Equation. You guys already know. Why am I doing all these things? Okay. So these are known as the system of the equations are not closed. Okay. So in order to close it, of course, you have to use the equation of state. Again, there are certain conditions when you can use the equation of state. You know, ideal when the densities are low, assuming the astrophysical fluids are quite dilute. So then only it can be approximated with the ideal gases. So now you have P in term. So basically, what the equation of the state tells you is it connect two thermodynamic quantities. Let's say P and rho. So you can get rid of one thing here, P with rho. So you are left with 4 unknowns and 4 equations. So you can always solve it. Okay. Yeah, but problem here is that if you use the equation of state, assuming the temperature is constant. Okay. But if the temperature is not constant, then of course you introduce one equation and then you have introduced one more unknown. Then what will you do? Yes, energy equation. So this, he already knows the entire fluid mechanics. But anyway, for others, we can discuss this. So first thing is, if you have a barotropic fluid, then I mean, P is a function of rho, then T can be also written as a function of rho. But if P is independent and rho is independent, then you need, of course, the equation describing the temperature evolution. And temperature is nothing but the internal energy in some sense. So basically, you need a energy equation, as he pointed it out. Okay. So for isothermal fluids, so these are barotropic fluids, by the way. For isothermal fluids, T is constant. You can use the equation of state. For adiabatic fluids, energy is constant. Still, you can use the equation of state because P can be written as some K into rho to the power gamma. Okay. But of course, for isentropic fluid also, I'm not going into the equations, but you can still use it. So in case of barotropic fluids, the closure is achieved by combining only 2 equations as well as the equation of state. Perfectly fine. But if the fluid is not barotropic, so then we need some other strategy to close the system of equation, and that's where comes the conservation of the energy. Okay. So so what does it, I mean, what this equation tells you, takes care of the heating and cooling processes causing change in the temperature, basically. So, or internal energy, you can say, temperature. Okay. So it can be derived using first law of thermodynamics, where you know that dq is a heat absorbed by unit mass of the fluid, and d is the change in internal energy where the temperature will come. Okay. And this is the work done by the fluid. You know, this is the first law of thermodynamics. Since there is a fluid, there is a pressure. So there is a PdV here. And then you can differentiate its equation. And you know that there will be a d bar here. What is this? You might have read about it. You know, intensive, extensive variables. So what is that? What does it mean? Yes, exactly. Okay. So I mean, you can go back and read about it. I don't have time again to go through it. So let us go to directly to the energy equation. Let me see where it is. So this is the total energy, which can be written as the summation of kinetic potential and internal energy of a fluid. Okay. Yeah. So let me, and then you can differentiate it. You can take a total total derivative of this energy, and then you end up in getting all this thing. So you do it on your own. I will share the slides, and then you see there is a term coming here, Q cool, which was not present here. So this term is the extra term that we have added. If there is some, if the fluid is also radiating away certain, I mean it is radiating, so the temperature will go down. Okay, so that is known as the cooling term. So that will also be added, and if there is some heating because of thermal conduction or something, that will also be added here. Okay, so that will all contribute to the rate of change of the total energy. So if you let me see, let me go to the final equation. So this is the final equation, of course, in the conservative form in some sense. So this is the total energy. Capital is the total energy. The rate of change is equal to the capital E plus P. This is the no. So I told you in the conservative form, if this is the energy density, so then it should be the momentum flux. Okay, so then that's why there is a U here. Okay, so E plus P comes from derivation. You see the derivation where the P is coming. Okay, plus it is here because there was a P term in, yes, in Bogdan as well as in the momentum equation. There was rho UU plus P del IJ. So, and then this is a potential. If potential energy change is 0, then this will not be there. And this is the cooling that is happening, which is obviously changing the energy. Plus, you can also add the heating term here or thermal, whatever you have. So all the sources and sinks will be here, and everything here is. And if there is nothing, there is no potential energy change as well as there is no cooling, there is no heating. Basically, the right-hand side is 0. So this is, of course, is in a conservative form. Okay, so you can say the energy is conserved in a volume where there is no heating, no cooling, and no change in the potential. So let us see, so let us list them down. So these are the fluid dynamics equation basically. So first one is the continuity, then you have momentum. Okay, I will come to the Poisson equation later on. Momentum, then you have an energy equation. Okay, and this is the definition of total energy. This is equation of state. This is internal energy. This is sufficient if you have a barotropic fluid, then you can solve the entire system. If not, then you need these three equations. Where is this one coming? Why you need this equation? No, this is the Poisson equation. There is no charges here. Okay, why you need this term? This is a gravitational potential. That's fine. But why you need this equation? Center force, yeah, of course, this gravity is a center force. But why you need this? Sorry.
Mass and mass left side force of things.
No. Can you think another?
Otherwise, there is not able to find the potential that is coming in the energy equation.
Exactly. There is external force, right? There is rho g here. How will you? And then, if the g is constant, then you do not need this. Okay. For example, if you have a gravity and then you want to study the behavior of the fluid in this room, but the gravity is not because of the fluid, it is because of the earth. Okay, so then rho g is the external force here. Okay, then g is constant. Then you do not need this. This term only comes when you have a self-gravitating body, right? In a self-gravitating body, the fluid that is under investigation is producing the gravity on its own. How will you solve for it? Because then this will be unknown. And how then there is one more unknown, so you need one more equation. So basically, you need the Poisson equation. So I mean, later on in the course, we use something known as gene instabilities, how the stars are formed because of the gravitational collapse. There you need this equation, but otherwise, in all other scenarios, you are fine without this equation also. It really doesn't matter. But then, I mean, for completeness, these are the list of equations which you should be using. Okay. Okay, so one of the consequence of probably you all might have read about it. One of the consequence of these momentum equation is the Bernoulli theorem, and this is also important when you will study the accretions around compact object. There you use the energy equation, which is along the streamlines, which is derived from the Bernoulli theorem. So let us understand what the Bernoulli theorem is. So and then after that, I think I will go to the first application of these equations in solar corona. Okay. So you start with this. Now this equation is now familiar to you. Then you do some sort of manipulation and you use a barotropic fluid. So yeah, you will end up here. For steady flows, steady flows means you remove all the time dependence here. Okay, so you end up in getting this equation, where phi is your gravitational potential. Gravitational potential, this dp by rho is half u square and u dot del. Okay, so and this term is 0. So it is only possible when this is constant, right? Okay. So this is your Bernoulli theorem. So where h is some constant. So what are the consequences of this Bernoulli theorem? Is so, but there's one important thing. You see, this is you are taking this dot product with u, right? So this term is 0 only in the direction. I mean, this entire expression is 0, basically only in the direction of u, right? So basically, that is nothing but the streamline. Assuming that the fluid parser of if it is moving in this direction, then your streamline is also in that direction. So this is constant only along the streamline. Okay, so don't think that if I mean, usually I give a question that you have a fluid parser and different fluid parsers have different streamlines. So if this h is a constant for one streamline, it cannot be put as a constant for another streamline. Okay, it is only valid only for a particular streamline. Okay. And it has a very important consequences when you study the airflow over the foils of or over the wings of an airplane. Okay, so don't blindly use the Bernoulli theorem there, because that is not valid. Okay, because those are different streamlines, so you can't really say that the pressure is small up and large down, and then it will cause a lift. That's a wrong explanation. So it is very important that it is valid only for a particular streamline. You have to first define your streamline and then apply Bernoulli equation. So here is the example. Okay, so here these are two different streamlines. Okay, and then if you apply the Bernoulli theorem, you see that the velocity here should be larger than this. Okay, because eventually it has to cover the larger distance. I mean, the distance is more here as compared to here, and the flow is continuous in both the directions. So it has to match here, so that u1 is greater than u2. So if you blindly use the Bernoulli theorem, p1 is less than p2, and then you have solved the problem of how the airplane lift, and this is the usual explanation, right? So, but the problem is that is it applicable in the real scenario or not? I mean, even in this scenario, of course not, because you have seen several planes moving upward, even if they are upside down, right? So how is it possible? Because if you have upside down, then this part will be here, okay? So then there should be a lift, not the lift, but it should sink down, but that is not happening, right? So, so the problem with this scenario is that you are assuming the h, which was constant, is same for this streamline as well as for this streamline, right? Then only you can make this argument, which can be true to some extent if you assume that in minus infinity and in plus infinity, okay, the flow is laminar, okay, and it is steady, not much changing with time. So you can assume that different streamlines have probably the similar constants. Okay, then you can apply that scenario here that if they have a similar constant, it will remain same here, and this H will remain same here, but these two are equal, so you can equate these two, and then you can make this argument. That is a fair argument. That is fine. Okay, you can do that, but then you have to assume that at minus infinity and plus infinity, the nature of flow is same, and you cannot distinguish between different streamlines, right? But then if it is different, then this scenario is not applicable. So it's a good textbook scenario, but in reality, it is not the case. In the reality, you really need to tilt the wings of the airplanes in order to get the lift, right? So that is known as the rotation. The airplane has to move up, and so that it will start getting the lift. If it start moving just the plane, then it is very difficult to get the lift. It's not possible. Okay, so this is an important, and that comes, there's, I mean, I don't want to go into the details of the theory of the airfoils, but we do teach during the course, but I'm not going to teach here. Okay, the second thing is, let us say you can apply Bernoulli theorem to understand the flow of water or any other fluid through the tap. Okay, so here you can easily use Bernoulli theorem. You know, now it is the same. You assume that the fluid parcels are from here are going in this direction. So this is a streamline, and this flow is laminar. These are the assumptions. If you do that, then whatever the pressure is here should be the pressure here. I mean, if you apply the Bernoulli theorem, half V square plus potential is here, it should be equal to this, and then you equate these two. So you will end up in getting this velocity, which is interestingly square root of 2gh. Okay. Of course, this is for the ideal fluid. If the fluid is not ideal, there will be viscosity, and it will not allow fluid to move up to that height. Okay. So there will be there will be cohesive forces also, which everything is actually ignored here. Okay. So so let us not. I mean, these are the questions, so let's not worry about them. Shall I go to vorticity equation? Okay, this will be more complicated. Let's not go here. Let me go to the application, because of course the core. So it's not here. Let me go to the third lecture then. Because here we said that we will study the application of these things in the solar corona. Okay. Yes. Okay, so we will now study this. Okay, so let us study the momentum equation and assume the case of a hydrostatics, right? So, so initially I told you different definition. The statics means that basically the time derivative is zero, as well as the velocity is also zero. If it is steady, then only time derivative is zero. U is not zero. But this is a static case, so both are zero. So if you start with the momentum conservation equation, in the presence of the gravity, then you will end up in getting this equation. Okay, assuming that all time derivative as well as velocity is zero. So under what condition can you solve this equation? Okay, so assume, I mean, the easiest thing is to use the barotropic flows. Okay, where the pressure is because you see there is a pressure here, density here, and potential here. But then if you use a barotropic flow, the pressure is dependent on the density. Okay, either it is isothermal flow, then P equal to rho kBT, rho to the power 1. Adiabatic, it is rho to the power gamma. Okay, so okay, let me, yeah. So for isothermal atmosphere, you know P is equal to rho kT. Okay, so instead of P, you can write rho kT, where kT is observed in this constant. I mean, this is some constant. So this is isothermal. So this is a simple constant. So we don't have to worry about it. So you see what you get. You get rho as rho naught e to the power minus mu g by RTZ. This is a question we were asking during interviews. No one was telling it. This is a simple hydrostatic equilibrium condition, right? What is the consequence of this equation? So you are now at Nainital, right? Which is at what height? 2000 meters. So how the density would change with height if the things are steady, assuming there's overall no velocity of the fluid, okay, and the temperature is constant. Of course, it is not constant, but assuming that it is constant, then this is how it should change. So density will drop. I think Krishna has already showed you about the scale height. So atmosphere, yeah, this is a different way of solving it through this. Also, don't. I don't know why you guys are confused, but it is essentially the same thing. Okay, so this is the scale height concept of scale height in the isothermal atmosphere. But the atmospheres are not always isothermal, right? So you can have. I have to cover waves also. Okay. Okay, maybe I need to. Maybe I need to go fast. So this is the case when you have when the gravity is constant, right? So here you are assuming that the gravity is because of the Earth, not because of the atmosphere of the Earth, right? So then you can make it a constant here, and then you can easily solve this equation. You can go back and derive the scenario where the gravity is also because, or gravity is because of the atmosphere, not because of the Earth. Then it would be a self-gravitating case, and then you will find some interesting solutions, which is way beyond these solutions. Okay, these are questions I gave. Okay, so so that is one thing, and another thing is again, you consider a hydrostatic and a steady fluid. That means del by del T is 0 and U is 0. Then again, you will end up in getting this equation del P is equal to rho F. That was one of the application. So one of the application of hydrostatic was that you get the scale height, okay, in the atmosphere, and this is the second application. So again, you start with the Euler equation, and then, okay, you do not have any barotropic fluid or anything. Okay, then how will you solve the equation? Of course, you need another equation, which is the energy equation that connects two different regions in the atmosphere, or it tells you the basically the time variation of the energy or how the energy is varying with the time. And this is the equation that we discussed before. This is the energy equation. Now here we are assuming that there is no energy transport process. So basically, this is the scenario of the solar wind. In the solar wind, we are assuming that the system is closed, there is no heat sinks. Okay, so then basically this part will go to 0, nothing else. Okay, so so this part is going to 0. There is no conduction. There is no thermal radiation. So what you are left with is this plus this some extra term is coming here, del dot K del T. This term is known as the thermal conduction. Okay, so what happens in that, in solar atmosphere, we assume that okay, so this is the solar atmosphere, this is the corona. Suppose the corona starts from the atmosphere is 2 megameter above only. Okay, so here the we are assuming that the temperature is like 1 million Kelvin. Okay, now because of this temperature, how the pressure will vary as you go away from the from the sun. So how the pressure will vary. So this equation, the energy equation, is telling you that how the energy will change. Okay, provided there is also a thermal conduction. Thermal conduction means you are allowing the energy to flow from here to here or from there to here, doesn't matter, but you are allowing thermal conduction, and at the base you have like 1 million Kelvin plasma. And because of that, what would be the energy equation that is given by the second equation? The first equation is simple, the Euler's equation. Now I assume that I mean, we are assuming that nothing is changing with time, so there would be a specific gradient of temperature, okay, which is given by this, okay, which is actually driving the thermal conduction, because if the temperature is same, then of course there is no thermal conduction here. Okay. So now everything is TD. So this term will go away. U is 0, this term will go away, so you are only left with this term. Okay, so you have two equations. One equation is this and another equation. This tells you the evolution of temperature. Of course, only the spatial, not the temporal, because we are looking at the steady case, and this is telling you the, of course, the gradient of pressure is equal to the force. Okay. So let us see what is that. You know what the F is. So here again, the important point is that the gravity is because of the, because of what? What is this term here? Gmm1r square. There's a so gravity is because of that, not because of the atmosphere. Then dP by dr you can write as P. You can write as P. Rho you can write as P by kBT here. So you have everything in terms of the pressure, and then you have this is the second term. And now this is only 1D. We are only solving in R, not interested in theta and phi. Okay, so let us see how it behaves in R. So if you do that, and you can do it on your own, okay, you will end up in getting this type of equation. Okay. This is only for the, I think, for the second case. Okay, so you'll get this relation T and T naught. That means how the temperature will vary with R. As I told you that here the temperature is large. So this is how it will vary with the radius. Okay, so T naught and R naught are the temperature at 2 megameter. I mean temperature at the corona, R equal to R naught. Okay, and T naught is a temperature at the corona, which is 1 million Kelvin. And of course, we are assuming here is what we are assuming here is that T goes to 0 at infinity. So if you plot it here, so this start at T naught, which is probably equal to 1 million Kelvin, suppose, and then it goes to 0 at infinity. Under that condition, you will get this type of relationship. Okay, so R to the power minus 2 by 7. And this was your, and then you use that temperature in the first equation. Okay, then you will end up in getting everything in terms of P, and everything else is dP by P, and here only the variable is R and dr. So of course you can solve how the P will vary with R. And then if you do that, you will end up in getting this expression. Okay, so this tells you that if you allow thermal conduction to be operative in the solar corona and in the steady case, then then the pressure will vary like this. Okay, I don't know what happened to that. Then the pressure will vary like this. So and this is of course the boundary condition. The problem here is that if you put R equal to infinity here, that means at an infinite distance, this term will go to 0, but this term will still remain. I mean, e to the, basically it will be e to the power minus 1, right? Minus something. So some variable. But then it will not be 0, basically. That is the most important thing. So that's the problem. The pressure will not vanish at infinity. So in fact, if you draw it, I usually ask student to, plot it. If you plot it, it will be like an asymptotic equation, like this only. And it will become, so at the very last distances, now you know what is the edge of our solar system, where the ISM start, interstellar medium. So at those distances, you can calculate what will be this pressure. And actually it was done. And what we found is that this pressure is much, much larger than the pressure of the interstellar medium. So what does it mean? It means that either our entire heliosphere is expanding, right? If there is no pressure which is opposing that, all the pressure at the, suppose this is where the ISM start. Now you can calculate what is the pressure here using this equation, and you know what is the pressure of ISM. So if this pressure of ISM is not equal to this, then of course the thing should expand here. So what they show, what you can show is that since the pressure is not constant, so there is a continuous expansion of the outer atmosphere of the sun, which is basically will culminates into the solar wind. Okay, so these type of winds are known as the thermally driven winds, because of course you are using the temperature here. There is no magnetic field here. If you continue to change the value of T naught, your P value will continue to change here, because of course, the T naught is here. So your value of the way this pressure will decay or pressure will decrease will change, and that will also change the velocity of the winds. Okay, that I am not showing here, but these are one of the very initial results by Parker. So what we found is that the solar winds should be present all the time. And of course, if you add a magnetic field to it, then it will become even more complex. At the regions of open magnetic fields or the straight magnetic fields at the poles, they become even faster. At other regions, they become slow. But overall, if you calculate the solar wind at 1 million Kelvin, it turns out to be around 400 kilometers per second using the simple calculations. Okay, so this is like one of the applications of hydrostatic, very simple. Okay, fine. So let us stop here. So I don't know how much I will be able to cover tomorrow. So let us stop here. So we have studied about the equations of hydrodynamics and one of its application. I'm not studying. I will not go to other applications, and tomorrow probably we'll cover 1 or 2 more topics, and then we'll move to MHD and its application. I mean, those who wants to go can go. They can ask tomorrow. Others can ask now. Yeah, they can go and they can ask questions tomorrow. Others can ask questions now, maybe for 5-10 minutes, and then I can. So tomorrow, I am thinking to cover the waves and then go to MHD and cover the MHD waves. Okay.
Other people, anyone wants to ask?
So we started with the question that the solar system is.
Okay, I
solar
forgot to
system is
answer
a
that.
fluid or-
But didn't you get the answer? So that is a continuum hypothesis, basically.
Yeah.
So if you have enough particles in hand, then you can invoke the theory of fluid, macroscopic theory. But in the solar system, if you want to study only the sun and 9 planets, there are only 9 particles.
Yeah.
So you can't do that. So you have to use probably the 3-body problem, 4-body, 5-body problems, something like which is even more complicated. But in galaxies, you can do like both using n-body problems, or if you are looking at larger scales, like in the kiloparsec scales, then you have enough stars in hand, which you can treat as individual particles. Then you can study them like a fluids. For example, in fact, the traffic flow is also modeled using the fluid. Why? Because if there are 1 or 2 cars, you cannot do it. Traffic means there has to be a lot of cars and a lot of buses, and I mean the particles that you want to study, or the system that you want to study, should have enough particles to behave like a fluid flow. So the answer is for galaxy, yes. For solar system, I thought okay, maybe I didn't go back to that question. So yeah.
Also, so I saw a bit on machine learning, using machine learning for fluid flows.
Using machine learning for fluid flows, for what?
So it was to understand fluid flows, and then they use it to like model the galaxies, collisions of galaxies. How are you doing in that?
I don't know. I don't work in that area, so I don't know how they are using machine learning to understand the fluid flows of colliding galaxies. But I mean, of course, you can always use these equations to study it. But how do you machine learning? I don't know.
Thank you.
Yeah.
Everyone wants to go.
Yeah, they already knew about it. Yeah, he has a question. I think it was very basic. Probably I should
Sir,
have.
what effects would we have to consider when the fluid is non-homogeneous?
When the fluid is not homogeneous.
Yes.
Well, from the mathematical.
Maybe mixture of one fluid is more viscous than something.
One fluid is more viscous.
And they are mixed.
They are
collective
mixed.
Dynamics.
Yeah, you are asking several questions in one question. I mean, more viscosity also, then mixing also. So there, I have not discussed here, but I must have one animation to show. Probably I will answer your question with that animation. Just a minute. So of course you have to. Right? Okay, so probably I will show the animation. Why to show the mathematics? Why aren't... So you see, okay. Yeah. So this is 2 different fluids. When I say 2 different fluids, means they have 2 different densities. They might have different velocities also. Okay. And of course, different viscosity can also be possible. Okay. In such a scenario, I mean, of course, there are only 2 fluids. There could be 3 fluids, more than 2 fluids. So in such a scenario, several different interesting effects happen. Okay. So there are different instabilities that can happen. Some of the systems could be stable. Some of the system may not be stable. For example, in this case, there are 2 different fluids with 2 different velocities, with 2 different densities moving past each other. So what happened? There will be a shear force, what we have discussed, and because of the shear force, there will be instabilities which is generated. And these instabilities are famously known as the Kelvin-Helmholtz instabilities. So probably you will see here. You see now? There's a lab experiment. And now there is a mixing here. in this. So what all you need to study this system? Well, that is not easy. You need a lot of complicated mathematics. You have to attend my class, probably. So then you consider like a lot of different things, density with different velocity. Of course, this is the famous Bernoulli theorem that we have discussed. So, I mean, you use these equations of, these equations only. But what you try to do is you try to match these equations at the interface, because of course there shouldn't be sharp discontinuities. And from there, you'd see the effects of these instabilities. And then if you have a very inhomogeneous, I mean, this is not really inhomogeneous plasma, it is piecewise homogeneous. There is one density and another density. If you have completely inhomogeneous plasma, then you have rho as a function of x, y, z, or rho as a function of r, p as a function of r. Then probably you need even more complicated mathematics. Probably analytical solutions are not possible. Probably you need to solve them in using numerical simulations. I mean, that is my point of view.
Sir, yes, I have this another question, and this might be a little out of context. Is sand sometimes considered as fluid?
Again, you use the continuum hypothesis, you can.
Yes.
Probably.
Because in making of glass through sand, we have to raise it to high temperatures.
No, sorry, what do you say? Glass to sand?
No, sorry, sand to glass. Glass is made up of sand.
But that is, I think that is a different thing. That's the phase of matter is changing in that case.
Yes. But
I thought you are saying that
sometimes, yes, regardless of this example, I have seen sand is being treated as fluid sometimes.
It can be, depends again, as I said, depends on your
continuum
hypothesis.
of that.
Yeah, it can. It's not really a fluid because I'm not sure whether it will resist the shear flow. Maybe it is not, it will not resist, but it's because of the interaction between different sand particles. But probably in some sort of problems you may. Yeah. But it's not a real fluid because it doesn't resist the shear flow.
Yes, thank you, sir.
Sir, due to that pressure calculation, if we calculate it for the Venus, so Venus will encounter some pressure, right?
Pressure at the distance of Venus.
At the distance of Venus. So, this pressure is significant to
displace. No, I don't think so. It is not even significant. It is not even realistic. Whatever calculations I have shown you is only for the ideal fluids, assuming energy equation under certain assumption. So this should be the case. This is indeed the case. You have solar winds in the heliosphere. So your question basically boils down to the fact that whether the solar wind, which is the consequence of this expanding corona, whether solar wind can impact the Venus and displace it from its. No, it is not like that. Of course, it can rip planets off its atmosphere. I think it happens with Mars. Because once it loses its magnetosphere, then the solar wind starts ripping off its atmosphere and got rid of its atmosphere after that. Yeah. But changing the trajectory of, I think it's too much to think.
Okay.
If your mathematics shows that it displaces, then it is wrong because Venus is still there. Any more questions?
Yes.
So you showed that experiment where some solids under constant shear stress will start acting like liquids, right? Mm-hmm. So do solar winds, like if with constant displacement, maybe not displacement, but because of the constant pressure, do they have the capability of like completely displacing the atmosphere?
Completely displacing
the outer atmospheres of planets?
Of Earth.
Of planets, like
that's what I said. I mean, solar wind can rip off the atmosphere of the planets, but for Earth we have magnetosphere.
Right.
So I mean, it deflects the solar wind. It is not directly impacted, deflects and going to the poles form auroras. But for other planets, of course, it doesn't have magnetosphere, and probably it can rip off the planets of its atmosphere.
I mean, but with magnetosphere also, like eventually, like.
Yeah, then you have to do simulations, I think, to know what time scales are needed to do that, to completely rip off a planet. At least in Earth, it has not happened in 4.5 billion years.
Yeah.
So, yeah.
What question? Not, we can, let's thank Vaibhav.
Okay, thank you.